Hi Year 13. I'm going to use this video to move along with M2. We're now on chapter 8, which is called Further Kinematics. And basically what this chapter is going to be about, it's going to be SUVAT but using vectors. So I'm going to start by recapping some of your kind of prior vector knowledge, and then we're going to start to apply it to things that we're doing in mechanics. So we're thinking about things moving across the 2D plane. So we're going to be using 2D column vectors most of the time. So the notation I'm going to use for vectors is going to be either a column like this, with A at the top, B at the bottom. Thinking of that as being our kind of usual arrow with A units along the ground and B units up the side. But then we've also got this these special vectors I and j that I've drawn on the grid as well. I being the vector 1, 0, pointing that way, and j being 0, 1, pointing upwards. And then any column vector that you like can be expressed as multiples of I and multiples of j. So it's easy to convert between these, as you've seen before. The column vector AB is just the same as AI plus B lots of j. Okay, so a question is going to kind of use these two notations interchangeably. I think it's better to use column vectors because it's easier to manipulate and easier to read as well. So let's, I think it's up to you to decide what one you want to use. Okay, in terms of notation as well, we've also got this idea of a position vector. So if I put an object on my grid and label it A, then the position vector of A is the vector that attaches itself to the origin like this, and it gives its position from the origin. So the notation for it is normally R, and it's the position vector of A. Okay, same goes for any point on the grid. Then secondly, if I were then to move from a position of A to a position of B, let's put it over here. So let's suppose I've done something to A and it's moved like that. Then I can also describe the displacement vector of B from A as well, and that's going to be this vector here. Okay, so there's a good distinction between these two. So I've got a position vector, which I suppose can be described as displacement from the origin as well. But a displacement from any point is given by a vector like this, and the notation is normally given as S, like that. Okay, so just make sure you know the difference between the two things there. Right, if we're then to use SUVAT using our vectors, we've got to firstly think about which of the 5 letters of SUVAT can be actually used as vectors, because not all of them can. So let's write these down. So for displacement, we're either using S or R. So it's SUVAT or RUVAT. Okay, so I've given a huge clue here as to which way is going to be which, but let's talk them through. R and S, these are position vectors or displacement. Clearly they're going to be vectors. Vectors being objects with magnitude and direction. Velocities, these are also going to be vectors. I can represent them as having velocity has magnitude and direction as well. Acceleration, similarly, they're vectors too. Acceleration is your change in your velocity over time in a given direction. T is the only one of the 5 that can't be a vector. Okay, this is the only one that's only a scalar. It only has magnitude, not a direction. Right, so effectively, if we think about our 5 SUVAT equations, we can typically replace all of our letters with these vectors and scalars here. There's only one that we can't use, and that's this one. This equation here, although it looks like we can substitute values and vectors into this, we can't actually square vectors or multiply them together in a meaningful way in this context. So this one is out, I'm afraid. So you can't use this one for reasons I've just discussed. However, the 2 most common SUVAT equations we're going to be using with vectors are going to be these ones. V is U plus AT, except A is not the vector A is. T is a scalar. And S is ut plus a half at squared. It's worth remembering those two and then knowing that they're the most common ones that are going to appear in a question. Okay, if you want to look up the other two, you can, but for now, I'm going to leave those out. Okay, before we move on to some examples, I think it's worth us getting one final equation that describes the position vector as well. So this is our kind of new equation that we can get using this. So I'm just going to get rid of this stuff on this grid and use it to kind of set up a new equation that we can derive. And then we can add that to our collection of equations that we can potentially use. Okay, so before I do that, it's worth us noting that in order to use SUVAT at all, you must have constant acceleration. Okay, otherwise these no longer apply, these SUVAT equations. On top of that, if you have constant velocity, there's a nice equation we can also get that describes position, as I've said before. So let's put a new point up. Let's call this point A. And let's give it its initial position vector here. So this initial position I'm going to label up as R0 for time being equal to 0. Now let's give it some constant velocity. Let's give it the velocity of 2 minus 1 meters per second. Okay, so that means every second we're going to be traveling along the vector 2 minus 1. So after a single second of time, we're going to be traveling along 2 minus 1 to get to here. And that gives us our position after 1 second. And then after another second, we're going to do another 2 minus 1 and get us down to here. Now we're here. And so on and so forth. Yeah, you can do another one of these and get to t equals 3. Great. So what we're after then is we're after some equation that describes our position after a certain amount of time. Now, if I put in a vector that gets us to where t equals 3, we can maybe discover how we're going to get that. So maybe let's call this R, but we're aligning it with t equals 3. So obviously this R vector depends on how many multiples of this velocity vector we've done. But in order to do that, we've first got to get from the origin up to point A using R0 and then add multiples of V. So I'm going to write down the equation here and hopefully you agree with me. So R, our position, is our initial position, the R0 vector, plus multiples of V, so plus t lots of the vector V. Great. Let's describe what all of these things are, and then we'll kind of highlight it as something that's important. It's worth you writing this down. So R is your current position. R0 is your initial position. That's where you started. And then t is obviously time, but with units that agree with the units you've got over here for your velocity. And v is your constant velocity. Like that. Okay, that's quite important, so it's worth you writing that down. Okay, so given any amount of time, you can start with this vector and add multiples of 2 minus 1, and you'll get some kind of position vector. I didn't actually give one for this, so maybe if I give it 1, 3, that will make it make sense. So given these numbers here, you can then work these things out. Okay, let's see an example of this working first of all, then we'll do some proper examples that use all these SUVAT equations. Okay, so I'll give you time to read through this. A particle starts from the position vector 3, 7 and moves with constant velocity 2 minus 1 meters per second. Firstly, find the position vector of the particle 4 seconds later, and then the time at which the particle is due east of the origin. Okay, seeing as it's our first example, I'm going to draw a picture so we can kind of see what's going on with this. So our particle starts at 3, 7. That's going to be roughly somewhere up here, 3 units along, 7 up. And then we're moving with constant velocity 2 minus 1. That's similar to what we had before. So we're doing this vector every second. Great. Okay, after 4 seconds then, we're going to have done this initial vector here, which is 3, 7. And then 4 lots of this, but I'm going to write that as a vector equation. So I'm going to set up my equation. R is 3, 7 plus t lots of my vector 2 minus 1. But then when t is 4, we can get our position. So that's 3, 7 plus, and then if I put the 4 into the bracket, I can then get myself 8 minus 4. And then adding the vectors gives me 11, 3. So that's my position after 4 seconds. Okay, which you can work out. You can add this and 4 of these. Okay, great. For the second part, there's a bit more to it now, and I think a picture is definitely going to help us again. So I'm going to draw a new picture. But this time I'm going to extend this to the point where my vector can get my position can get down onto the x-axis, if you like. So again, starting here, this is 3, 7. And then we're moving along our velocity vector until we get down to here. Okay, so hopefully you agree. At this point here, this is where I'm due east of the origin, because I'm pointing that direction out of the origin. And my position at this point is going to look like something like this. It's going to be some I coordinate on the top, and then it's got to be 0 on the bottom, because that's the only way that I can be due east of the origin, is if I'm on the x-axis where the j's are 0. So if I can express this using algebra, I can then solve it for t. But according to what I've written on this line, I can write an expression for my position vector. It's going to be 3 plus 2 lots of time. That's combining these two vectors here. And then 7 minus t along the bottom. Okay, given that the j component is meant to be 0, I can then look at the bottom of this vector, set it equal to 0, and solve for t. And it's clearly 7. And we're done. So these questions are quite common. If you're asked to figure out when you're due east or some compass direction from the origin, you've got to be thinking about what that means in terms of the components of this vector. Sometimes you can set them equal to 0. If you're moving, for example, in a northeast direction, then whatever your position vector is, so I need to rephrase that. If I'm due northeast of the origin, I should say, because that's different. If I'm due northeast, like this, then again, my position vector is going to be some set of components, but seeing as I'm due northeast, then the components have to be equal because the number of i's equals the number of j's. So that's the way that you would go about solving a problem like that. So it's worth noting then that this is the picture for what it means to be due northeast of the origin. However, that's different from having a velocity vector that's due northeast, because I could be over here, and if my velocity is going in this direction, then my position won't be due northeast, but my velocity will. So there's a distinction there. Okay, I'm going to move on to the next question. Okay, this final one has quite a lot of different examples, some of which are going to use SUVAT and some of which are going to use our previous example. And hopefully it's going to make sense. And if you've got any more questions, you can drop me an email. So let's get started. A boat moves with constant acceleration. That's a good start because that means I can use SUVAT. And we're starting at the origin. That's also quite helpful when it comes to at least writing displacement down as well. Okay, my initial velocity is 30 meters per second due south. I'm going to highlight that all in one color because it all contributes to my velocity vector. That's going to be u. And then 1 minute later, it has a velocity of 45 meters per second due east. That's going to be my v. And the east and south are going to be important because they're going to tell me what my two-dimensional vector is going to be. I and j are what they normally are. They're just unit vectors directed east and north, as we normally expect. And then I've got this 1 minute later as well, which is my time. Bearing in mind that this is given in minutes, whereas my velocities are given in seconds. So there's going to be some kind of change of units there. Okay, firstly then, the acceleration of the boat in terms of I and j. Now I've got v, u, and t. If I want to get a, I think the best SUVAT equation to use is this one. Let's sub those in. So v is this red one here. That's going to be 45 meters per second due east. That's the direction, and it's going to be pointing out to the right, due east. So that's going to be 45, 0. And that's going to equal u, which is 30 meters per second due south. If I'm pointing south, that's downwards. So my velocity vector is going to be 0 minus 30. And then plus time is going to be 1 minute, that's 60 seconds. And then my acceleration vector is going to need to have two components, so I'm going to put a1 and a2 for the acceleration. Okay, now it's a matter of solving. I'll leave you to do that to save a bit of time, and it turns out that a1, a2, by solving and rearranging, is going to be this. It's going to be 3/4 and 1/2 meters per second squared. Great. Okay, that's A done. B, the position of vector of the boat at time t seconds. Now, we're going to interpret position vector as being displacement from the origin. Seeing as we start at the origin, it makes sense to have my displacement vector as being that position vector. So S, displacement from the origin, is ut plus 1/2 at squared. Okay. Yeah, think of S as being displacement from where you started. Okay, let's plug things in then. So ut plus 1/2 at squared. U, I need to get this right. This is my 0 minus 30. That's times by t as well. Plus 1/2. And then my velocity, sorry, my acceleration I got over here, that's 3/4 1/2. And then times t squared. Great. Okay, I want that ideally written as a single column vector, so I can maybe use it again later. So I'm going to distribute my scalars into the brackets and then combine together. So I'm firstly going to get 0 minus 30t. And then I'm going to add it to 1/2 and t squared inside gives me 3/8 t squared, and then 1/4 t squared. Now I can add together, that's going to give me 3/8 t squared on top, and then minus 30t plus 1/4 t squared on the bottom. And that's my position vector after t seconds. Okay, great. Okay, for C, the velocity of the boat at time t seconds. I just need some way of writing down the velocity with t seconds, but that's clearly going to be done by using this equation from part A again. So my velocity is u plus at. That is going to be u, again, 0 minus 30. I'm going to not going to use the colours anymore because I don't think I need to. Plus acceleration, 3/4 1/2. Times t, and then combining into a single column vector gives me 3/4 t, and then minus 30 plus 1/2 t. Great. Now, part D, the time when the boat is due east of the origin. So I think a quick picture here is going to be useful to us. So as before, we're due east of the origin, so somewhere here. This is going to have a position vector of something 0. But our position vector is the same as our displacement from our start, seeing as we started at the origin. So that's just given by this vector over here. So what we're looking at is this vector here for our displacement, t squared minus 30t plus a quarter t squared. But then it's only the bottom part that we're interested in, making it 0. So that means that minus 30t plus a quarter t squared equals 0. Let's set it equal to 0. Then it's just a basic quadratic. I'm going to factor out t first of all. So t lots of, I'm going to swap the order as well. That's going to be a quarter t minus 30 equals 0. And then that means that t equals 0, or t equals, what's this going to be? 4 30s is 120, which is 2 minutes. Okay, now I suppose we're not sure about how the question's worded, but we can disregard this one because this is where we started. We started at the origin itself, which is here. And then after 2 minutes, we ended up here. So we're definitely due east when we get to this point. So I'm going to go for this one. Oops. There we go. Right, so this is our non-trivial answer, if you like. Great. E, 2 more to go. The time when the boat is traveling in a southeasterly direction. Okay, so this is different to part D, because part D was talking about a position, whereas part E is talking about a velocity. So direction you should associate with your velocity vector. So let's think about where we got our velocity vector. That's going to be over here. So let's write our velocity vector again. 3/4 t minus 30 plus a half t. That's my velocity. And if we're traveling southeast, let me get this right, southeast points this way. Now what that's going to mean is that you've got equal magnitudes on these legs, except the vertical component will be the negative of the horizontal component, or vice versa. So these are going to have opposite signs. So basically you're going to have this component, and then this is going to be the negative of that component for this to work. So what I'm going to do is I'm going to set the top equal to negative of the bottom. So 3/4 t is going to be the negative of minus 30 plus a half t. Okay, hopefully you can see what I've done there by using this picture here. In other words, you can think of it as being parallel to 1 minus 1. That's another way of thinking about it. Maybe I'll write that over here. So whatever you've got, the top is the negative of the bottom, or vice versa. This gives us an equation to solve, so let's do that. I'll maybe get rid of this over here. Okay, so what does that give us? That gives us 3/4 t equals 30 minus a half t. If I then add a half t to this side, I'm going to get 5/4 t equaling 30. And then timesing by 4 gives me t equals 120, and I'm going to divide that by 5. That is going to give me 24 seconds. Great. So at that moment in time, that's when your velocity is pointing in that southeast direction. Okay, home straight, let's do F. The position vector of the boat at the time when it's traveling in a southeasterly direction. Okay, so another distinction here. This is position now, not velocity. So our position's got to be southeast. So a picture might help. I want to have a position down here somewhere where from the origin we're pointing southeast, which is also S. Okay, so back to our displacement vector. That's this one. So back to this displacement vector. Let's write it out. So you've got 3/8 squared. You've got minus 30t plus a quarter t squared. And again, this is going to be minus 1 on the bottom compared to what's on top. So the top is the negative of the bottom. Let's write that as an equation. So 3/8t squared is the negative of minus 30t plus a quarter t squared. Okay. Solve the quadratic equation. Let's go. So 3/8t squared is 30t minus a quarter t squared. Let's add everything onto the left side maybe. So what's this going to give me? This is going to give me 3/8 plus 2/8 will be 5/8 t squared minus 30t equals 0. I guess we should probably times by 8. I don't like the look of that fraction. So 5t squared minus 240t equals 0. Okay, I'm running out of space. I'm going to go teleport over to this top left side and finish it off. I'm going to divide by 5 after I've written this out again. So 5t squared minus 240t equals 0. Divide by 5, t squared minus, I believe, 48t equals 0. I'm going to double check, just I want to finish the video off without making a mistake. Yep, good. Factor out t and we're nearly done. Okay, so t equals 0, this one t equals 48. But as we had before, at the very beginning, when t is 0, we're at the origin. I don't think that counts as travelling in a southeasterly direction. Do you know what? I've got this last one wrong. I thought I'd get right to the end of this, but I didn't. That's very, very, very annoying. Okay, you have to bear with me. I'm going to do this last one again. I'm not going to do another half-an-hour video just to get to this point again. Okay, we could have done this a lot much more simpler. Very frustrating. That's okay. We can do this very quickly at the end. Okay, I should have maybe read this question a bit more carefully. So we've got from part E the time that we're traveling in this southeasterly direction. And then this is the direction again. We know the time. I just want the position vector at this time. So we need our position vector. 3/8 t squared minus 30t plus a quarter t squared. And then all we've got to do is put in when t equals 24. Okay, sorry for wasting a little bit of time there, but we're just about done. So 3/8 times 24 squared is 216. And then 24 into the bottom gives us minus 576. Okay, that's our position, and we're done. Great, we got there in the end. Thank you very much, Year 13. I hope you get on all right with today's questions. If not, please give me a shout. Thanks very much.